Good afternoon and welcome to your very last unit of Stat 220. Congratulations on making it this far. You are almost done. And in our last unit, you are going to find some similarities to what you saw in Unit 9 because they are essentially two different methods of answering the same question. So in Unit 9, we talked about confidence intervals, which allow us to take a sample and use our results to get an idea of a range of numbers that represent what is possibly happening in the population at large. Hypothesis tests do the same thing, okay? So hypothesis testing is what we are looking at in this unit, and hypothesis is a word that you're definitely familiar with, but you probably haven't seen it in a math class before. You probably think of that word being more associated with your science classes, and what you will find is that it has the exact same meaning as it did in your science class. So let's look at how a hypothesis test actually works before we try to run one. So first of all, you can do a hypothesis test for proportions or for means, just like you could do a confidence interval for proportions or for means. But in either case, you are going to have two hypotheses. Okay? So let's look at our example here. Calcium is a vital nutrient for healthy bones and teeth. The National Institutes of Health recommends a calcium intake of 1,300 milligrams per day for teenagers. However, the NIH is concerned that teenagers are not getting enough calcium on average. Is this true? So first of all, I noticed the word average in this problem, and that tells me that when I set up this hypothesis test, I am looking at the mean, not a proportion. Okay, so what do I call my two hypotheses? Well, the first hypothesis that I write is what's called the null hypothesis, and that's the one right here. That's the H with the little zero. Your null hypothesis is a statement of no change or no concern. So in this case, the null hypothesis is that the average is what it should be, that it actually is 1,300 milligrams. Okay, but then we also need to think about, well, what if that's not true? What's the alternative hypothesis? And that's the H with the little a here. Well, the alternative, or what we're concerned about, is that the mean is actually less than 1,300. And this is what we call a left-tailed test, because numbers that are less than fall on the left side of a bell curve, right? So if we had been concerned about teachers getting too much calcium, we would have flipped that less than to a greater than, and now it would have become a right-tailed test. So what happened here? Well, some researchers decided to actually perform this test, and again, I will show you how to do that in your calculator later. And they asked a random sample of 20 teens to record their food and drink consumption for one day. And I want to pause right there. If you remember what we talked about in previous units, that is a very small sample size, and I would want to proceed with caution because technically I can only assume that my data is normal if my sample size is at least 30 people. So I would have to be checking some other different graphs and things to actually make sure that my data was normal here. I could not just assume that based on a sample size of 20, right? Okay, so here's what the researchers find. They find that their sample average is 1198 milligrams, which is clearly less than 1,300, so they're concerned, right? And the standard deviation is 411 milligrams. So they perform a significance test, and they obtain a p-value of 0.1404. So let's talk about what this means. What would the null hypothesis mean in this setting? If the null hypothesis comes out to be true in our test, in this setting, that would mean that teenagers on average are okay. They are getting 1,300 milligrams of calcium on average like they're supposed to. What does the p-value mean? Well, our p-value is the probability of getting the results that we got from our sample purely by chance, even if the null hypothesis is true. So how likely was it that just by chance we got a sample result of 1198 if teenagers actually do get the calcium that they're supposed to get? Well, it was about a 14% chance, right? Which that's not incredibly high, but it's not really unusual either for something to happen 14% of the time, right? So then what is our conclusion? Because our p-value is 0.1404, which is not highly unusual, and what I mean by not highly unusual, there was a greater than 5% chance, and that's generally our rule of thumb. Sometimes you may see people say, look at a 10%, and the way you tell is right here. They told us alpha is 0.05. So anything less than 0.05 is considered unusual. Okay? Because of that, we fail to reject the null hypothesis. So notice here, I didn't say that the null hypothesis is true. There's no way from one sample of 20 people for me to guarantee that the population of teenagers at large is getting enough calcium, right? But I'm saying based on the sample that I have, I can't reject the null hypothesis, right? We don't have convincing evidence that teenagers are not getting enough calcium. So I never use the words true or false in these situations. I either say that I fail to reject the null hypothesis, or in some cases, I may have enough evidence to reject it. So now that you've seen what the setup looks like, let's actually run a hypothesis test. So let's say that I told you that I am an 80% free throw shooter. Well, first of all, because I'm seeing percents, I know that this is going to be a hypothesis test based on proportions, not a mean. Okay? So what's my null hypothesis? Well, my null hypothesis is that I told you the truth, right? That I actually am an 80% free throw shooter. And the way that I would write that is P equals 0.80. But then let's say that I go out in front of you and I shoot 20 free throws and I only make 13 of them, right? Well, that's definitely not 80%. That's only 65%. So what are you now thinking? You're thinking I may have lied to you. So your alternative hypothesis is that P is actually less than 0.80 based on the free throws that I just shot in front of you. So again, what I want to remind you of is if all that I tell you is that I shot 20 free throws, that is too small of a sample size for you to just assume that your data is normal. So what I did on number 2 to justify that I had normal data is I actually looked at what's called the normal probability plot. And again, that's not something you have to know in here, but that's how I made sure that my data was normal before I proceeded with this test. What else do I have to check? I have to make sure that my free throw shooting was random, right? Which we can kind of assume that. There's nothing really controlling whether I hit this shot or not. Either I miss it or I make it on my own merits, right? So that's pretty random. I also have to assume independence, which means that 20 has to be less than 5% of all free throws that I shoot. I mean, that's a pretty safe assumption that 20 is less than 5% of all the free throws that I've ever shot in my life. So now that I have verified that all my conclusions hold for running this test, I am going to calculate the mean and standard deviation. Well, we are going to assume, until told otherwise, that our mean is 80%. Okay? How do I find my standard deviation when I'm dealing with proportions? It's that same formula that you saw when dealing with confidence intervals. It's the square root of P times 1 minus P over N. And when I plug that in my calculator, I get a standard deviation of 0.089. Okay? Now, if my standard deviation is 0.089 and my mean is 0.80, what I want to do is calculate my z-score for my sample data. So my score for my 23 free throws was 0.65. I'm taking that minus what I said, which is 0.80, to see how far off I was from what I told you, right? And then I'm dividing that by my standard deviation to give you a z-score of negative 1.69. What does that mean? That means that I am 1.69 standard deviations below the average, right? So it's looking pretty good that I may not have told you the truth, okay? So then in my calculator, what I did to get the p-value is I used that normal CDF button because I verified that I have normal data, and I looked at everything from here to roughly somewhere right in here, right? Because that's between 1 and 2 standard deviations over here. So somewhere right in there. And so when I went into normal CDF, I did negative 1,000. So that's just some really big number that represents the fact that this curve never ends. Up to negative 1.69. I said my mean is 0 and my standard deviation is 1 because that's the way that z-scores work. And I get a p-value of 0.046. So what conclusion can I make? Because my p-value was less than 0.05, I can reject the null hypothesis. There is evidence to suggest that I lied to you, that I actually shoot below 80%. So again, notice I did not state for sure that I lied or that I told you the truth. I said I am rejecting the null hypothesis. Okay? Now, what is a shorter way that I can do this so that I don't have to work it all out by hand? Well, let's look at another example, and we'll do this one in our calculator. So let's say that according to the U.S. Census Bureau, the proportion of students in high school who have a part-time job is 25%. However, an administrator at a local high school suspects that the proportion of students at her school who have a part-time job is less than that figure. She would like to carry out a test at the alpha equals 0.05 significance level. What does that mean? If she gets a p-value below 0.05, she's going to consider that unusual. Okay? She's going to reject that null hypothesis. So the administrator selects a random sample of 200 students from the school and finds that only 39 of them have a part-time job. So what are our hypotheses? Well, the null hypothesis is a statement of no change, or in other words, there's nothing to see here. And this school matches the population percentage of 25%. So our null hypothesis is p equals 0.25. But what does this administrator think might be true? She thinks p might be less than 0.25. That's our alternative hypothesis because she doesn't yet have any evidence to back that up. Okay? All right. So let's talk about, and again, we're going to check this in our calculator, but why does the sample result give some evidence that the alternative hypothesis might be true? Well, when you look at 39 out of 200 students, that's only 19.5%. That is quite a bit lower than 25%, right? And the other thing that gives this test more power or more ability to back up what this principal is saying is that she used a pretty large sample size. She had a sample of 200 students here, right? So let's check if our conditions for reporting the significance test are met. First of all, was it random? Yes, I know that because the problem tells me that they were randomly selected. Is it independent? We have to make an assumption here that 200 is less than, I know the notes say 10%, but we're going to say 5% because that's what my lab asked for. We have to make the assumption that 200 is less than 5% of all students at the high school. Without knowing the size of the school, there's no real way for us to know for sure, but we're going to assume that for the time being. And can we assume the data is normal? With the sample size this large, yes, we can, because n times p times 1 minus p comes out to be 37.5, which is larger than 10. Okay? Now, for part D, I'm actually going to show you how to run this test in your calculator so that you don't have to do all of the calculations by hand. So let me get that pulled up. Okay? So, once again, we are going to go into our distribution, or excuse me, we're going to go to our stat menu, and we are going to go over to test, and because this is a proportion, we are going down to option 5, which says 1 proportion z-test. So how do I enter this in? So this little p0, that 0 is there because it's referring to our null hypothesis. So what do we think the proportion is, or what has it previously been stated to be? 0.25. Okay? What is our x value and what is our n value? X and n are referring to our sample. So in our sample, there were 39 students out of 200 who had a job. This next line is referring to your alternative hypothesis. So what did we think might be true? We think that this school might have less than 25%. So we're going to click the less than option. And you may not have the color option. That's not a big deal. There are 2 options here, calculate and draw. I'll show you what they both do. So if you draw, what it does is it actually draws the normal curve for you. And it highlights the part that you are actually looking at, and that can be kind of useful. That's not something that is always asked of you, but sometimes it is asked of you on my lab, so that is something that you could look at. It also, at the bottom, spits out your test statistic, which in this case is a z-score, and it spits out your p-value right here. So it kind of gives you everything that you need. If you go to calculate, it gives you this information but without the picture. So that's up to you whether you click calculate or draw. But for now, what I'm really focused on is the p-value. Okay, that p-value is 0.0362. So then what conclusion would I make? Well, because my p-value is less than 0.05, this time we have enough evidence to reject the null hypothesis. And again, we're not saying the null hypothesis is necessarily false. We are saying there is evidence to suggest that less than 25% of students have a part-time job at this school. Okay? All right, we are going to skip the next page. We're going to go to our very last example, and let's talk about how this one is a little bit different. So it says the level of dissolved oxygen in a stream or river is an important indicator of the water's ability to support aquatic life. So a researcher measures the DO level at 30 randomly chosen locations along a stream. Okay, so why is that important? Well, first of all, our sample size is 30. So we can assume that our data is normal when we run this test. Okay, here are the results in milligrams per liter. So from the sample of 30, this researcher found that the average DO level was 4.77 with a standard deviation of 0.939. An average dissolved oxygen level below 5 puts aquatic life at risk. Do the data provide convincing evidence at the 0.05 significance level that aquatic life in the stream is at risk? So there's a lot of numbers going on here. Here's where I want you to be careful. When you write your hypotheses, right, they are both based around the same number. And that number is going to be the number 5. That number that goes with your null and your alternative hypothesis comes from the population at large. It does not come from your sample. Okay, so what is my parameter here? So my parameter, or in other words, what I'm measuring is mu, or the mean. And I know that because what was measured was x bar. Okay, so x bar is the sample mean. That's what's actually measured. So what are my hypotheses? Well, the null hypothesis is that everything's hunky-dory, that mu equals 5, and we're good to go. Our alternative hypothesis is that mu is less than 5. And that's concerning because we may start to see issues in aquatic life if it's less than 5. Okay? What's our significance level? 0.05. So what type of test are we running here? Well, this time, since we're dealing with means, we are going to run a t-test. Much like when we did a confidence interval that dealt with means, we built a t-interval. Okay, so what are our conditions here? Well, we already checked our sample size. Because our sample size is 30, we can assume that it's normal. Were these streams randomly chosen? Yes, I know that because it tells me. And then the last thing I need to check is independence. And again, we have to make some assumptions here. We are assuming that 30 is less than 5% of all the sites that could have been chosen along this stream. Okay, so let's go to our calculator and actually run our test here. Okay, so I'm going to go to Stat. I'm going to go back to that testing menu, and this time I am running a t-test, and that is the button you click every time when you are dealing with means. So I run a t-test. If you had raw data, so let's say you were performing an experiment yourself, you would enter the data, but we don't have that. We have stats. So I click stats. What is mu 0? So that comes from our null hypothesis. That is 5. That's what we're hoping is still true, right? However, what we suspect or what we are worried about is that it's less than that. And so that's because our sample average was, let's see here, 4.77. And then our sample standard deviation was 0.919. Okay? And then what was our sample size? Our sample size was 30. And again, for our alternative hypothesis, we are selecting less than because our sample results indicated that it might be less than what we previously thought or desired. And when I draw this picture, for some reason it is trying to graph something else here. There we go. There's our normal curve. I'm not sure why it tried to give me something else on this picture as well. But there's our normal curve right there. Okay. And this time, instead of giving us a z-score, it gave us a t-score. And our t-score was negative 1.37. What does that mean? We were 1.37 standard deviations below that average of 5, right, that we would want. Okay, so what is our p-value? Our p-value is 0.0905. So let's think about that for a second. That means that we had roughly a 9% chance of getting a sample average this low purely by accident, even if this stream actually was okay. While that is low, it's not really incredibly unusual, right? What we're looking for is a p-value below 0.05, and we didn't get that here. Okay, so what is our conclusion? Our conclusion is that because our p-value was greater than 0.05, we fail to reject the null hypothesis. We don't have enough evidence to suggest that the DO level is actually below 5. All right, so there you have it. You have completed all the videos for STAT 220. Please let me know if you have any questions.